Okay, so for today, guys, kind of was looking over the quizzes, and I've had a number of people who've come in to get some help with naming and things like that. And what I'm kind of seeing as a pattern here is that people are kind of getting lost in the steps, okay, on their way from name to formula or formula to name. And so I went through the notes and I'm like, yeah, I really don't have like a set of steps for people to follow, so it kind of makes sense that people might get lost between kind of start and finish on those. And so I sat down and I've built up kind of a list of steps that you can follow when you're naming a compound or when you're writing the formula for a compound. So what I want to do is, first off, have you write this down. So there's kind of two columns here. This is for writing chemical names. Okay, so if I can get you to write those down, and then we'll walk through a couple of examples of that, and then at least you have something, okay, that you can follow if you're struggling with that and you're trying to practice it at home. Maybe this can help you to kind of keep on track or make sure you're doing the right steps. Okay, so I'll give you a couple minutes to get those ones written down, and then I say we'll walk through a couple of examples. Okay, so let's just walk through a couple of examples here of writing the name of a chemical formula. All right, so let's say that I have this name here. Let's say I have, or sorry, this formula here. Okay, and I'm supposed to write the name of that. So if I'm kind of walking through and following my steps, the first thing I need to decide is it ionic or molecular? Because the rules for writing those are different. Okay? In molecular compounds we use prefixes, and in ionic compounds we don't. So what I need to look for is if there's a metal listed first. If there's a metal listed first, it's ionic. Is calcium a metal? It is. Okay, so this is an ionic compound. So now I'm going to go over here to the ionic side, okay, and follow the rules here. It says ionic, write the name of the metal. So next thing I do, write the name of the metal. Okay. Third step, write the name of the nonmetal. Make sure it ends in "ide." Okay, this stuff is phosphorus. Phosphide. Okay. If there's a polyatomic ion, write its name as it appears in the table. Are there any polyatomic ions in this one? There are. Okay. If the metal has more than one charge, determine the Roman numeral. Does this one need a Roman numeral? No. Calcium is always a 2+. It only has one possible charge. Okay, I'm done. All right, that's all there is. Now, that's the easiest an ionic compound can be. Okay, is not having any of those other rules to worry about, but that's how we would do that one. Okay. If I got, let's say, this one instead, I'd probably be looking at all of the rules on this one. All right, so first off, go back to step one. Is this ionic or molecular? It's ionic. Copper is a metal. Okay, write the name of the metal. All right, well, so I'll write copper. Okay. Write the name of the nonmetal. I don't have a nonmetal. I have a polyatomic ion. So I got to go down to, if it's a polyatomic ion, write the name as it appears in the table. Okay, SO4 is sulfate. Okay, so I don't change it to "ide. I write it as it appears in the table. Does this one need a Roman numeral? Yes, copper can be a 1 or a 2+. All right, so I use the non-metal, in this case my polyatomic ion, to determine the charge on copper. According to my table, sulfate is a -2. Okay, how many sulfates are there? 1. Sulfate is SO4. It has 4 oxygens and 1 sulfur, but there's only 1 sulfate here. Okay, that's why we use those brackets, right? If I'm going to have more than 1 sulfate, I'd have to put brackets around it with a number outside the brackets. Okay, in this case, there's only 1 sulfate ion. All right, so there's only 2 negative charges here. So I need to get 2 positive charges from the copper, and there's only 1 copper. So what's the charge on this copper? 2. So then I put a Roman numeral 2 in there. And that would be as hard as they would get. Okay? That would be the toughest one. it has both a multivalent metal and a polyatomic ion. Okay, questions there? Okay. What if I had I don't even know if that compound exists, I just wrote something with some numbers. Okay. P3O8. Is that ionic or molecular? It's molecular. They're both non-metals. All right, so step 2 for molecular, write the first non-metal's name. Phosphorus. Okay, write the second non-metal's name ending in I. Oxide. And I left some room because I have to put prefixes on here. What prefix needs to go on phosphorus? Tri. Okay, and what needs to go on the oxide? Octa. Probably didn't leave enough room. Octa oxide. Okay. Everybody all right with how that works? That's all there is to molecular. There's no tricks. It's just prefixes and that's it. Okay, is that making a little more sense if we have a set of steps to follow? Okay. I mean, you're not going to get to have these steps on a quiz or a test, but at least if you have them while you're practicing, you'll get the hang of it and you'll kind of know the steps and be able to do it on your own. Okay. All right. Other things I was seeing as kind of patterns here, and it's just stuff that you're going to have to commit to memory, but I was seeing people use prefixes in ionic compounds. Okay, that's a big no-no. We never use prefixes if there's a metal present. Right, so we have to make sure that we're remembering that rule. It's an important rule. Okay, so here's the rules for writing formulas. Okay, so the first rule is determine if it's ionic or molecular. That's the first rule regardless, okay, because the rules are different for how we do it. If it's ionic, then we write the metal symbol and the charge, write the non-metal symbol and the charge, drop and swap, reduce if necessary. If there's polyatomic ions, we'll need brackets. Okay, if it's molecular, we write the symbols for both non-metals and put in the numbers from the prefixes. So I'll give you a minute to write those down and then we'll walk through a couple of examples. Okay, so let's walk through a couple of examples of this one. All right, so let's say I have this name. Magnesium nitride. Okay, so step 1 is I'm supposed to determine whether it's ionic or molecular. If there's a metal listed first, it's ionic. What's this? Yeah, it's ionic. Magnesium is a metal. Okay, so I know now I've got to go to step 2 for ionic. Write the metal's symbol and charge. All right, the symbol for magnesium is Mg and its charge is 2+. Write the non-metal symbol and charge. Okay, nitrogen is N and its charge is -3. Okay, drop and swap. All right, so what that means is take this number, drop it, and swap it. So the 3 will go on the magnesium, the 2 will drop and swap and go on the nitrogen. Mg3, N2. Okay, step 5, reduce if necessary. Can't. If polyatomic ions, don't have any. Right, I don't have to do the last 2 steps. Everybody all right with that? Okay, try nitrogen monofluoride. Ionic or molecular? Molecular. As soon as I see prefixes, it's molecular. Okay, so next step, write the symbols for both nonmetals. N, F. Okay, using prefixes, place appropriate numbers in the formula. Tri is the prefix for what? Mono is the prefix for 1, but I don't write ones. Okay, done. N3F. Give it out. All right, let's do one that's maybe a little bit hairier. Cobalt-3 carbonate. Ionic or molecular? It's ionic. Cobalt is a metal. Okay, so I've got to follow the ionic rules. Write the metal symbol and its charge. All right, so the symbol for cobalt is CO. What's its charge? 3. It can be a 2 or a 3, but the Roman numeral is a 3, so its charge is 3. That's what the Roman numeral tells us. Okay, and carbonate. Since it doesn't end in "ide," where am I likely to find it? In the polyatomic ions. Okay. Okay, CO3, and its charge is -2. All right, so now I need to drop and swap. So the 2 is going to drop and swap and come right here, and the 3 is going to drop and swap and go right here. All right, what do I need to do since I just put a number beside a polyatomic ion? Brackets. Right, that's what that one would look like. And that would be about as tricky as they would get. It has both the Roman numeral and the polyatomic ion needs brackets. Okay, is that a little easier to follow? Okay, so if you're still struggling with that, now you got these steps. You can, kind of follow them as you practice and get more right and kind of feel more confident in your ability to do that. And if you're still struggling with it, come in and see me. Okay, next week, Monday morning, Monday after school, Tuesday at lunch, Tuesday after school, Wednesday, Thursday, all 3 times I'm here. Okay, just pop in and see me if you're needing some help. All right. Going to talk a little bit about solubility here today, okay, because it's part of our lab, but it's also something we need to understand for just for chemistry in general. So if I can get you guys to find in your notes package lesson 8 on solubility and the properties of water. We're not going to get to the properties of water today, but we will get the solubility stuff likely done today. Okay, so for solubility, a lot of solubility is just knowing the terminology. Okay, so knowing the definitions of certain terms. The other part of solubility is being able to use your solubility chart, which is on the back of your periodic table. And so if you flip your periodic table over, you'll see like a data sheet that's got a bunch of physics formulas on it, and you'll see a solubility chart on the left. Okay. We're going to be learning how to use that solubility chart today. It's pretty straightforward. It's nothing terribly difficult. But it allows us to determine whether when this metal and this non-metal are together, if that ionic compound will be soluble or not. Okay? That's what it allows us to determine. Most ionic compounds are soluble, but there are some that aren't, and that chart allows us to determine which ones are and which ones aren't. Okay? All right, so for the start of this, okay, some substances dissolve easily and some don't. We know that. We've all mixed stuff together before and seen things that do dissolve and see things that don't dissolve, right? If you've ever, mixed oil in water or put butter in water or something like that, it doesn't dissolve. You can get it to, float on the top. You can get it to sometimes get in there a little bit, but it'll eventually separate again. Okay, if something is always going to separate, regardless of how much agitating or heating or whatever it is you do to it, it is considered to be insoluble, okay, which means not soluble. If you can get it to dissolve and stay dissolved, then it is soluble. Solubility is a physical property. That's why it's one of the things we're testing for in our lab on Monday. Okay? Some things are soluble, some things aren't. Okay. Now, here's some of the terms. Okay? If I have a solution, then I have a mixture that contains a solute, that's the thing that dissolved, completely dissolved in a solvent. That's the thing that did the dissolving. Pretty much all the time for us, our solvent is going to be water. water is often referred to as the universal solvent, which is terrible because not everything dissolves in it, and universal implies that, but, okay, that's what we call it. So when we're talking about solubility, it's almost always going to be about something being able to dissolve in water. Now, we know that not everything dissolves easily in water. If it did, we wouldn't need solvents. Okay, solvents are the things that we add to water to make stuff dissolve better. So, for example, if your mom or dad says your shower is disgusting, please go clean it, and you go in there and there's like a layer of soap scum this thick, okay, and you're looking at it and going, well, water is not going to get rid of that on its own, otherwise you could just turn on the shower and it would disappear, okay? But that's not how it works. So instead, you got to get out the vinegar or the CLR or, I don't know what else you might have, maybe muriatic acid. It depends how thick it would be. You got to get these things out that are going to help the water dissolve that material. Soap scum is not terribly soluble in water, okay? Which is why we have to add a solvent to the water to help it dissolve better. Follow me there? The other kind of thing we can have is a heterogeneous mixture. So a solution where something is completely dissolved looks like this on the left. Okay? This thing here on the left has only one visible part. Okay? And that's what homogeneous means. Okay? The prefix homo means one or singular. Okay? In this case, this is a homogeneous solution because it only has one visible part. There's more than one thing there, but they are completely dissolved in one another. Okay? Everybody with me on that? Okay? This, on the right, is a heterogeneous mixture. Okay? Hetero means many. Right? So this has more than one visible part. This stuff did not dissolve in here. Okay? So that would be a heterogeneous mixture. So a solution is a homogeneous mixture. Right? A mechanical mixture is a heterogeneous mixture. Okay? It is possible in a mechanical mixture to suspend one of the materials in the other, but eventually they're going to come apart. All right? And they can be easily separated. If I get something to completely dissolve in something else, I can't separate them as easily. Okay? I couldn't just take that mixture there on the left and run it through a filter and have the stuff come out. It's dissolved. It'll go through the filter. Everyone with me on that? How many people have made coffee before? Okay. I mean, this is the process by which coffee is made. Okay? You have the coffee grounds, the hot water goes through the coffee grounds, and some of the stuff that's in the coffee grounds dissolves in the water. Okay? The filter catches all of the grounds, okay? The chunky stuff, which I actually like having in my coffee. But okay, the last swallow of coffee is always the best because it's the chewy one. Okay? That's where all the caffeine is. That's what keeps you going. And if you've ever seen like real coffee, like Turkish coffee, it's all like grounds. So if you're really desperate, you just eat the ground. No, don't do that. It tastes terrible. Okay, so you get the water to go through, and all of the stuff that's in the coffee grounds dissolves, okay, but the grounds get left behind, okay, and so you get this mixture that's brown. Okay? Everybody okay with that? Okay, so some of the stuff in there is soluble. It doesn't come out in the filter. Okay? The stuff that's not soluble, the grounds, comes out in the filter. Okay. The only way I'd be able to separate now, if I had my coffee, the only way I'd be able to now separate, let's say, the sugar from the rest of the coffee would be to boil off all the water. Okay? If I boil off all the water, it'll leave behind all the stuff that was dissolved in it. That's the only way I can separate a homogeneous mixture. A heterogeneous mixture I can separate with a filter. Okay, or by some other simple physical means. So let's say I had iron filings and sand in a container, and I wanted to separate them. How could I do that? What physical property could I use to separate iron filings from sand? Yeah, I just put a bar magnet in there and stir it around. Okay? Eventually, all the metal filings would be stuck to the magnet, and the sand would be by itself. And you'd be able to separate them pretty easily. Okay? Everyone all right with that idea? Okay. Now, other terminology here, solute. Okay? A solute is the thing that gets dissolved. Right? So if I'm making coffee, it's the coffee or the sugar, okay, or whatever else is going to go into that mixture and disappear. Right? So it is the thing that's being dissolved. The solvent is the thing doing the dissolving, and as we said, most of the time that's going to be water. If I'm using oil-based paint, like stain, like you use on a fence or something outside, okay, if that gets on your hands, soap and water won't take that off. You need a different kind of solvent. You need paint thinner or bar salt or something like that. That will be the solvent that dissolves that stuff. Questions on those terms? Okay, would these be like super likely to show up on a quiz because they're fill in the blank kind of things? Yeah, or multiple choice questions on a unit exam. Okay, is where I would test terminology. All right, a precipitate is any solid that is produced in a chemical reaction and will not dissolve. When we do our reactions lab in a week or so, okay, our reactions lab is going to involve putting things together, mixing them together. And we're going to have a couple of reactions where you take two clear solutions, mix them together, and all of a sudden you get like a solid material that falls out of the solution, out of the mixture. That is a precipitate. And I'm going to show you what that looks like here in just a minute. Okay? It's called a precipitate because it falls out of the solution like precipitation falls out of the sky. That's what I mean. Precipitate means to fall out of, basically. Right? So I'll show you what that looks like. Now, there's like this really strange like background music on this video. It's this like weird Italian guitar music that's like, I don't know, mournful or sorrowful or something. It really doesn't fit with the video, but all right, so that's what a precipitate is. So if you ever hear the term precipitate, it means something that was formed in a reaction that is no longer soluble and thus forms a solid and either falls out of the solution or floats to the top. Okay, but in either case, it separates from the rest. Okay, now the term solubility means the degree to which a substance will dissolve in another substance, and it is a physical property. Some things are more soluble than others. Okay, it doesn't mean they're not soluble, it just means some things are more soluble than others. Okay, and that can be affected by the properties of the substance as well as temperature. It can also be affected by agitation. Okay, we all know that if you stir something, you get more of it to dissolve. Right? But if you cool it off, then less of it will dissolve. Okay? Like when I was a kid, I used to make Kool-Aid. Okay? You just mix the Kool-Aid crystals and sugar, but I would always make it with hot water because you could get more sugar to dissolve. Then you put it in the fridge, and when it cools off, you get this layer on the bottom. Okay? If you got that layer of sugar on the bottom, you knew the solution above it was saturated. That means you could not dissolve any more sugar in it. It was as sweet as possible, okay? Because no more would dissolve in it. The rest had precipitated out and was sitting on the bottom, okay? And that's when you knew it was good. I don't think you could see that. All right, so some things are soluble, some things are not. Some things should be soluble, some things should not, okay? Now, the example I'm going to give you here is the modern Twinkie. Okay? The original Twinkie was made from real ingredients. Right? And I'm not one of these people that says everything I eat has to be organic because I eat like crap. Okay? So I'm totally not one of those people. Okay? And I'm not trying to say you should eat better because that would be totally hypocritical of me. But Twinkies used to be made out of natural ingredients. They were, after all, cake with filling. Okay? So they were made from things like milk, eggs, flour, sugar. Okay? Now, the problem with making things out of natural ingredients is their shelf life. If they're made out of natural ingredients, they're going to spoil quickly. So if you can't sell them fast, they go to waste. And then you lose money. So shortly after World War II, Hostess, the company that makes Twinkies, changed the recipe for a couple of reasons. Strawberries were in short supply. They actually used to have strawberry fillings. Strawberries came in short supply for whatever reason, and they couldn't get them as much, so they filled them with the white filling instead. Okay? Well, the white filling was made of different materials. It wasn't the strawberry puree anymore. Okay? It was this like sugary frosting almost, which contained things like butter, okay? and sugar and lard probably, okay? Stuff like that. By doing that and not having the fruit, they actually increased the shelf life. They added in a couple of other things, preservatives we call them, okay, to increase the shelf life to about 14 days, which was much greater than a Twinkie would have in its natural form, 3 or 4 days. Okay. In the interest of being able to produce more of them and have them last longer, they started looking at things that they could replace eggs, milk, and butter with that would last longer on the shelf. Well, thanks to modern science, we can find replacements for eggs. Okay? All we need is some sort of protein substitute that will do the same binding that an egg will do. Okay? We can have modified milk ingredients, okay, instead of real milk. That won't spoil nearly as quickly. Okay? So we have all of these substitutes. But the big thing was substituting the eggs. The eggs and the milk were the things that spoiled. They did find an albumin substitute for eggs. Problem is, what color are Twinkies? They're yellow. Why are they yellow? Because they used to be made with eggs. Eggs are yellow. Once they substituted for the eggs, the Twinkie looked like it was made out of drywall. It was gray. Didn't look nearly as appetizing. People didn't buy it because it didn't look like a Twinkie. It looked like a piece of wall. So that was bad. So they replaced it or added to it yellow dye number 5, which is a known carcinogen. It means it causes cancer. Okay? It's actually banned in like the entire European Union. You can't put it in food. Right? But in North America you can because it makes Twinkies yellow. But it's not good for you. In, of course, large amounts. Unless you're eating a dozen Twinkies a day, it's not going to hurt you. If you're eating a dozen Twinkies a day, the yellow dye number 5 might not be the biggest worry. Okay? This 12 Twinkies a day would be really bad for you anyway. But yeah, they've replaced all these ingredients. So now the modern Twinkie is actually soluble in water. If you put it in a glass of water, it will literally dissolve. Okay? The original Twinkie would have done what cake does. Sucked up all the water and just became mush. Okay? But the new Twinkie, most of it will actually dissolve. So if you ever break your jaw and you have to have it wired shut, Twinkies are something you could still eat through a straw. Hey, you'd be surprised. Okay, I've known a few people who've broken their jaw and had it wired shut. They get hungry enough, they'll blend anything. Okay? They'll put a steak in the blender. And yeah, it's I can't imagine eating a steak through a straw, but you gotta eat something. Okay? So that's how you do it, because you can't chew with a broken jaw. Hey, making sense? I just wanted to gross you out a little bit. Show you a semi-partially dissolved Twinkie. Okay, let's have a look at our solubility chart. Now I think yours actually looks a little bit different from this one. So. Okay, so if you guys can all have a look at your solubility chart, please. It looks like this. Okay, guys, back of the periodic table, left-hand side, okay, is your solubility chart. Now, here's how your solubility chart works, okay? You've got a row here on the top, and in this top row are your negatively charged ions, okay, that could be part of an ionic compound. In the rows below are your metals, or positively charged polyatomic ions, okay, and it's set up like this. The second row is the stuff that is very soluble. Okay, so if what you're looking at is in the second row, it's very soluble. If it's in the bottom row, it's only slightly, or we just say not soluble. So what you have to do with these, I'm just going to bring this over here, guys. Just give me a sec. Okay, so here's how this chart will work. Let's say I'm asked to find out whether this compound is soluble. Let's say they give me this, lead to iodide. And they want me to find out, is that soluble in water or not? Okay, so the way I do that is I find iodine on the top row. I look for the non-metal or the negatively charged part of the ionic compound. So iodine is right here. Okay? Then I go down that column. It says that iodine is soluble with most things. Well, that's helpful. Okay? So it's soluble with most things. So if I see the word most, I got to look at the next row because I got to find out if what I'm dealing with isn't part of most. So I go down to the next row and I see that things that are not part of most are copper, silver, mercury, and lead. So that means that this compound here is only slightly or not soluble in water. Okay? And in fact, lead 2 iodide is a bright yellow powder. Okay? And we'll actually form it in the lab that we do next week. Sorry, not the one on Monday. The next one after that. Okay? Everyone kind of follow what I did there. Okay? So I just look at my compound, I find the non-metal part of it, and then I look to see what it's soluble with. So let's try another one. Let's try calcium sulfate. Okay, would that be soluble or not? Slightly soluble. And actually, let's just have you guys right now on your periodic table, cross this right out where it says slightly soluble and just say not soluble. Because that's basically what we say. Okay, it's either soluble or it's not. So it's in the second row, soluble. Third row, not. All right, so that one is soluble. We find sulfate is right here. It says, again, soluble with most things. But the first thing listed in the not soluble row is calcium. So that stuff would be not soluble. All right, let's try this one. Sodium carbonate. Soluble or not? It is soluble. Here's carbonate. Sodium is in group 1. Okay, group 1 is the first column on the periodic table. Okay, so that one would be soluble. All right, we'll talk more about that on Monday.